Welcome back to multivariate calculus. In this video, we're going to be differentiating a vector-valued function. Much like in our discussions on limits and on continuity, the derivative of a vector-valued function is going to behave very similarly to the derivative of a function of real values. And so let me get my head out of the way and let's start there. We know that for a function which maps from the real numbers to the real numbers, the derivative of the function is defined by the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. And we know how to deal with limits, and we know how to deal with everything else here. So we should have a very similar definition for a vector value function. And in fact, we will define it exactly the same way. We're going to define r prime of t as the limit as delta t goes to 0 of r of t plus delta t minus r of t all over delta t. And just like we saw in our discussion of limits, I claim that the derivative of the vector valued function given by components x of t, y of t, z of t is going to simply be the component by component derivative. X prime of t, y prime of t, z prime of t. Thankfully, the proof of this theorem is far and away more straightforward than the proof of the limit theorem from the earlier video. By definition, the derivative here is the limit as delta t goes to 0 of the fraction, which is the vector formed by evaluating at t plus delta t. So that's x of t plus delta t, y of t plus delta t, and z of t plus delta t minus the vector r of t, which is just x of t, y of t, z of t. Sorry, I'm running about a little bit out of space there to get the end, but that's just the x of t, r of y of t, z of t that we had to start with, all over delta t. Now, performing some operations on vectors. When you subtract vectors, you subtract component by component. So this is really the limit as delta t goes to 0 of the vector with x component, x of t plus delta t minus x of t. The y component is y of t plus delta t minus y of t. And the z component is z of t plus delta t minus z of t. And when you divide a vector by a scalar, you divide component by that scalar. So this is the limit as delta t goes to 0 of the vector with x component, x of t plus delta t minus x of t all over delta t. Y component is y of t plus delta t minus y of t all over delta t. Z component is z of t plus delta t minus z of t all over delta t. And finally, when you take the limit of a vector, you can take the limit component by component. And I'm really going to run out of space on this one. So I'm going to write this as component limit delta t goes to 0 of x of t plus delta t minus x of t all over delta t, y component the same, z component the same. Technically, yes, you should write them all out, but I'm out of space. And looking at the x component gives us everything we need because this is exactly the definition of the derivative of x of t. So we get x prime of t. And I didn't write it out, but it would be exactly the same, just replacing x with y. So that's going to be y prime of t and z prime of t. Much easier proof than the limits proof that we saw earlier. All right. But that means that taking derivatives of vector valued functions means learning almost nothing new compared to taking derivatives of scalar functions that you learned in Calc 1. So if I have the derivative to take of the function t squared I minus sine of tj minus cosine of 2t k, I can take derivatives component by component. The derivative of t squared is 2t. The derivative of minus sine of t is minus cosine of t. The derivative of minus cosine of 2t is, well, derivative of minus cosine is sine, but we've got a 2t, so we use the chain rule and get 2 times the sine of 2t in the k direction. Nothing new. All of the rules for taking derivatives work exactly the same as all of the rules that you've already learned for taking derivatives. I guess where things get a little bit interesting is when we want to extend the chain rule. We can take reparameterizations. We've talked about that before, where we take r of t and replace it with r of some other function, maybe s of t. And Well, I know what the chain rule looks like for a real valued function. We've already just used it in the previous example. And I claim that the chain rule is going to work the same for a vector valued function. The derivative of r of s of t will be s prime of t times r prime of s of t, which is a little bit backwards from how you would write the chain rule for a real valued function, but we have to write it this way. A lot of notation that we're going to be using here is based on head bashing stupidity. We've defined what it means to take a scalar multiplied times a vector. We have not defined what it means to take a vector multiplied times a scalar. In one order, the multiplication is well defined. In the other order, the multiplication is undefined. So in this case, when we have the scalar function s prime of t and the vector valued function r prime of s of t, we have to write it in that order in order for the multiplication to actually be defined for us. All right, but this is a theorem, so it should have a proof. I'm going to prove this by just saying that, well, we have a chain rule for real valued functions. So r of s of t equals component-wise x of s of t, y of s of t, and z of s of t. So r prime, I shouldn't write that way, I should write the derivative with respect to t of r of s of t is component by component. The derivative of x of s of t is x prime of s of t multiplied by s prime of t. The derivative of y of s of t is y prime of s of t times s prime of t. And the derivative of z of s of t is z prime of s of t times s prime of t. There's a common factor of s prime of t in all three terms, so we can bring that out. And we recognize that the stuff that's left is, in fact, the vector valued function r prime at s of t. Right, that's a very straightforward one, but one that will be useful to us. We're going to be looking at vector valued functions, and we're going to be looking at reparameterizations like this. But for our purposes, it's generally going to be in a very abstract sense. Unlike the chain rule for a real valued function, the chain rule for a vector valued function is not actually ever useful for, is not actually ever useful for evaluating the derivative. Instead, it's going to be useful for talking about the derivative when we don't know the value of the function, but we know that we have a reparameterization. Likewise, there are several rules involving products, quotients, and so on, right? The product rule for scalar functions, for real valued functions, is fairly straightforward. In vectors, we have three different options. And we should have a product rule for each option. So if I have two vector valued functions, and I want to take the derivative of r of t dot with u of t, well, I know what the product rule for scalar functions is, and I'm going to project that it should work out the same here for the vector valued functions, and then we'll prove that. For the dot product, we don't have to be all that concerned. We do have to be concerned that the dot actually shows up on the touch screen. We don't have to be all that concerned about order because the dot product is commutative. R dot U and U dot R are the same thing. That's not going to be true for the other products that we have available. And so it's worth trying to keep straight the notation. Since we have R dot U, we will have R prime dot U and then R dot U prime. Again, it's the product rule for real valued functions, just a little bit different looking because we have a dot product showing up in there. But it's also a theorem, so we had better be able to prove it. There are a couple of ways you can prove this one. I think that the easiest is to think about R of t in its components. X of t, y of t, I'm getting ahead of myself. X of t, y of t, z of t is how we've been defining R of t. And then we have u of t, and we kind of ran out of letters. And so I'm going to use f of t, g of t, and h of t just to give it some letters. I've also seen this done with alpha, beta, and gamma. I've seen it done with various other Greek letters. There's no one rule for what to use next. If x, y, and z are done and you need new coordinates, usually it's u, v, and w, but u is also the second choice for a vector valued function after r, so we can't use that because we already used u. So f, g, and h. It's 3 letters in a row. That's all we really need. And if I take r of t dot u of t, I get, and at this point, I'm going to suppress all of the of t's. I know that each and every one of these is a function, but I'll get x times f, I'll get y times g, and I'll get z times h, all of those functions of t. And so if I want to take the derivative of r dot u, again, everything functions of t, I'm suppressing the of t because it's just too much writing and everything is just a function of t and it's not like I'm going to forget something along the line. So the derivative of r dot u would be the derivative of xf plus yg plus zh, and I can take the derivative of each of those using the product rule for real valued functions. I will have x prime f plus x f prime. I will have y prime g plus y g prime. I will have z prime h plus z h prime. Nothing too crazy going on here. I can regroup this stuff to have x prime f plus y prime g plus z prime h together, and then x f prime, y g prime, and z h prime together. And I can recognize that those are exactly the result of taking the dot product of r prime with u and taking the dot product of r with u prime, which is exactly what I said I was going to get when I started off here. All right, so that's one product rule. There are 3 product rules because there are 3 different ways that you can multiply things when it comes to vector valued functions. We could have a vector valued function multiplied by a scalar function. in which case the derivative of f of t times r of t is f prime of t times r of t plus f of t times r prime of t. And given two vector valued functions, we can also take a cross product, and we can get that the derivative of r of t cross u of t is r prime of t cross u of t plus r of t cross u prime of t. For these two functions, for these two orders of multiplication, the order does matter. For the multiplication of scalar functions, as I mentioned earlier in this video, a scalar function or a scalar times a vector is defined. A vector times a scalar is not defined at all. So we do have to make sure it's f prime of t times r of t, and then f of t times r prime of t. It is still addition, so we could put those two terms the other way, but always f then r, the same way it's set up in the original. With the cross product, we have different things to worry about. Let me get my head back out of the way so you can actually see the cross product behind me. But the cross product is defined with an order, right? R cross U and U cross R are two different things. And since it's R then U, in our result, we always have R then U. R prime cross U, R cross U prime. Again, you can put those two in the other order if you'd like, but it has to be R then U, R then U. And these are the ones that I would like you to look at. Specifically, the scalar function times a vector function, I would like you to prove on your own. If you have time and you're interested, I encourage you to take a look at the cross product rule, but it's really messy and I don't think it's worth the time and effort to try to go through that proof on your own. The second rule here gets the idea across without getting you bogged down with pages and pages of algebra because, you know, it's cross products and cross products are unpleasant. If there's one thing you know about cross products, it should be that. All right, so try writing out the proof, go through the derivation, and verify for yourself that this product will always have this derivative. See what you can do with that, and I'll see you in the next video.